Greetings to you all. Welcome to Shex's YouTube channel. Um if you like the stuff that I normally upload to this channel, please press on the like button, uh, comment, share, and don't forget to subscribe. Um, my name is Martin Mashiga, and I'm taking you through number systems today. Uh, Let me just emphasize again about liking, commenting, sharing, and subscribing. So let's get into today's business. Today we're going to cover binary numbers, base conversion, number systems like ones complement, twos complement, and analog to digital and digital to analog conversion. And the first thing that we need to talk about is why should we talk about all this? Why should we talk about all this? So I will talk about binary numbers. Why should we understand binary numbers? The first thing to think about is computers understand zeros and ones. Computers understand zeros and ones. If computers understand zeros and ones, then why do human beings needs to understand the binary numbers? We need to understand binary numbers because we design computers that understand zeros and ones. So therefore, for you to design a competitive device that understands zeros and ones, you have to understand the zeros and ones. We design systems that work with zeros and ones, so we are forced to understand zeros and ones. So the form of communication here is saying all computers work with zeros and ones. So it is like learning alphabets before learning English. So it's more like the computer is learning. We are allowing ourselves to learn, so we come up with best designs. Why base conversion? Why should we convert decimal values to binary or binary to decimal values? Mm, We understand that computers understand zeros and ones. And these computers, as they understand zeros and ones, they perform all their calculations or computations using the zeros and ones. But what they output is something that is not in zeros and ones. It comes up as something that is human readable and that can be understood by human beings. For instance, we can have meaningful text, we can have computer visuals such as images and videos, but in the processing stage, the processing uh, task is done in binary. But now there is need for us to convert the binary to something that is meaningful and understandable by human beings. So for convenience, people use other bases like decimal, hexadecimal, and stuff. And we need to know how to convert from one number system to another, or from one base to another. And then why do we need to understand number systems? There are more than one way to express a number in binary. So for instance, we have 1010, which could be minus 5, which could be minus 2, which could be minus 6, depending on the number system. Therefore, you need to understand which number system are we dealing with so that you understand which of these three digits or three values is represented by the binary value that we are seeing there. And then why should we understand analog to digital and digital to analog conversion? We need to understand this because the real world is represented in an analog way. But when we want to do the computations about what is happening in the real world, we do it using digital signals or digital computations. Therefore, we need to understand analog to digital and digital to analog. So digital to analog is now, after computations, we need to throw some signals back to the world, of which what we understand in the real world is analog, and then we need digital to analog conversion. So real world signals come in continuous or analog format, and it is good to know generally how they become zeros and ones and vice versa. Right. Let's now talk about binary coded decimal. So that's the BCD. BCD numbers they make use of 4 bits to represent one decimal digit, which means a 4-bit binary coded decimal number can represent 10 states, which starts from 0 to 9. From 0 to 9. From 0 to 9. So those are the 10 digits the 10 values that can be represented by a 4-bit BCD number. And then an 8-bit BCD number can represent 10 to the power 8 divided by 4, which means an 8-bit BCD number can represent 800 states. As you can see that 4 is 10 to the power 4 divided by 4 gives us 10, meaning to say 4-bit BCD number can represent 10 states, 0, 1, 2, up to 9. Same applies to 32-bit BCD number, which can represent 10 to the power 32 divided by 4, which means it represents 100 million states. Right. BCD numbers encode less information than binary numbers with the same number of bits, as 6 of the 16 possible states are not used for each 4-bit BCD. All right, so you will see when we start to look at some examples how this is actually different. Because when we say we want to represent 2, right, let's say we want to represent a value that has got 2 digits like 24 using 4-bit 4-bit using 4-bit BCD. 2 must be represented by its binary values, and then 4 must be represented by its own values, meaning to say 2 4 should be represented by 8 bits and cannot be represented by 4 bits in terms of binary coded numbers. Therefore, it shows that BCD represents less information than the binary values using the same number of bits. All right, so mathematically each BCD bit, each BCD bit only encodes 10 to the power 1 over 4, which is 1.7 or 1.8 states, while each binary bit encodes 2 states. You can see that 2 is actually greater than 1.778. So the larger the BCD number, the more bits BCD coding wastes. For example, if you were to make a counter that counts 0 to 9,999, as you project, as you will see with a project that we are going to look at, with a binary counter, you would need 14 bits. Excuse me. As you can see, we have 2 to the power 14, which gives us 16,384, which is greater than 10,000. So using a BCD counter would require 16 bits. So as we can observe here we have 0 being represented by that. This is 4-bit BCD code. Now we talk about binary numbers, but we just make use of base 2, base 8, base 10, and base 16. So you can see when we are doing addition in base 2, we say 1 plus 0, we get a 1, 1 plus 1, we get a 0, and carry 1, 0 plus 0, 0 plus 1, carry it, we get a 1, 1 plus 1, 1 0, we write 1 0 here. And then when we are working with positional number system, for instance, we have 101 to base 2, we can have it written that way: 1 times 2 to the power 2. As we can say, 1, how many digits after 1? 2. Therefore 2 times 2 to the power 2, that's 0 times 2 to the power 1, and then 1 times 2 to the power 0 to get a value in base 10. Same applies for 63 base 8. We say 6 times 8 to the power 1 plus 3 times 8 to the power 0. Same applies to hexadecimal values in the base of 16, A1, 10 times 60 to the power 1 plus 1 times 16 to the power 0. We work in binary as well. 1 minus 0, we get a 1. 1 minus 1, we get a 0. 0 minus 1, it can't. We then carry 1. 1 minus 1, 1. Then a 0, since we then put a 1 after carrying. And then the answer is 0, 1, 0, 1. Now, the conversion from binary to octal or hexadecimal. So the binary value, that one, that's the one that we are converting to octal. So to convert to octal, what you do is you have to divide the values into those partitions. So this is just one. Partition this value into 1, 2, 3, 4. 4 partitions. So 0, 1, 0, 0, we get 1, and then 0, 1, 1, we get a 6 with this, and then 1, 1, 0, we get a 3, and then 1, 0 represents a 2, so that's why we get 2, 3, 6, 1. That's how we convert binary to octal. Then converting from binary to hexadecimal, we divide into we divide the number into groups of 4 each, from the right to the left. So this one we get a 1, that's why we have a 1 there, and then these 4 we get a 15, which is F, we put an F there, and this one becomes a 4, we put a 4 there. So that's how we get 4F1 base 16. Conversion from base X to decimal, for instance, from base 2 to base 10. I think I've showed you how this is done in the previous slide. And then I think I've showed you this as well, but now we have a point here. So whenever we go after the comma or after the point, we then put to the power minus 1, and then if you have another value here, we put minus 2, and we get that value. Same applies here. We do 10 to the power 16, 10 times 16 to the power 1 plus 1 times 16 to the power 0. Here we are saying 10 because A is representing 10. A is representing 10. And then here that's binary, converting decimal to binary. So this is the first one. So here what we are doing is we are saying we have a quotient and a remainder. So we say 50, we are converting from binary, which is base 2, to we are converting from decimal, which is base 10, to base 2, which is binary. So what we do here is we say 56 divided by 2, we get 28, and remainder is 0. 2 into 28, we get 14, and remainder is 0. 14 divided by 2, we get 7, and remainder is 0. 7 divided by 2 is 3, and remainder 1. 3 divided by 2, we get a 1, and remainder 1. 2 into 1, we get a 0, and remainder 1. Now what we do next is we read this value from bottom to up, so we can get this value is our answer. So this is 56 in base 2. So the same applies if we want to convert to octal. 56 divided by 8, we get a 7 minus 0. 7 divided by 8, we get a 0 remainder 7. And then, so we do this, we do the same. We count the remainder from bottom up. And then we get this answer is our solution. 70 is 8 is equal to 56 base 10. And then representing negative numbers, there are three methods that are used to represent negative binary numbers. We can use sign and magnitude. We can use 1's complement, or we can use 2's complement. So these are the methods that we use for all three. For all of the three methods that I've mentioned there, the most significant bit is the sign bit. When we say the most significant bit is the bit that is appearing as the first digit or as the first bit, or in other words, we can say the last bit counting from the right to the left. The last bit, that's what we're referring to as the most significant bit, and the last number or the last bit from left to right is the least significant bit. So here we are saying the most significant bit is representing the sign. It is representing the sign. So a 0 is representing positive values and a 1 is representing negative values. So 2's complement is the important one and is the most chosen one. Now let's look at the sign and magnitude. Sign and magnitude. Right, so sign and magnitude. The most significant bit, MSB, is the sign bit. So that's it. And the remaining bits are the numbers value or the numbers magnitude. So we have two sections. The first part is representing the sign, and the other part is representing the value or the magnitude. So problem number one, that's the problem with this sign and magnitude number system. We have two representations for the value 0. For a number, for a 0, which is a positive 0, we have 4 zeros. And then for a number, for a 0, which is negative 0, we get 1, 0, 0, 0. And then the other problem we have is the arithmetic is cumbersome. You do an addition, you get a value which is not the actual answer, or which is different or not equal to the actual answer. For instance, mostly when adding, it doesn't cause a problem, but mostly when you are doing the subtraction and blah blah blah, that's where you will find that the answers won't be the same. For instance, here we have 4, which is, let me open the calculator here. 4 let's convert from decimal to what? To binary. And let's just convert 4 here. Convert 4 to binary. So this is 4 to binary, right? So this is 4 in binary. And 4 in binary here, it's 0, 1, 0, 4 bits. Plus 3, which is 11, 0, 0, 1, 1. You get the same value, which is let's convert